This video lesson is going to talk about the energy of phase changes. What we've talked about so far in the calorimetry lesson, we learned about the energy required to heat up a substance so long as it is purely in the liquid phase or purely even in the solid phase or in the gas phase. But we're going to be talking about now about the energy required while a substance is changing phase from either a solid to a liquid or a liquid to a gas, or even for a solid directly to a gas as in sublimation. So the first phase change we're going to talk about is fusion. And what fusion really is melting. Right? It's just sort of a technical word for fusion. It's just melting. So this is the heat that it requires to melt something. So the definition that we can write here is it is the energy required to melt specifically 1 gram of the substance. The energy required to melt 1 gram of a substance. The reason we do that is so that we can compare substance A to substance B. If we're comparing 1 gram of each substance, then you can understand it takes more or less energy for one substance to melt compared to the other. Now, the symbol we are going to use for this is H, which makes sense for heat. And we're going to have a little sub F. So this stands for the heat of fusion. The unit for this is joules per gram. It's the amount of energy to melt 1 gram. So that unit hopefully makes sense. It's the number of joules to melt 1 gram. Now there's a mathematic formula that we can use to calculate the heat of fusion, and this is a formula that is found on reference table T. So if we look at reference table T, under heat, we have the calorimetry equation, which we worked with previously, and now we are looking at Q equals M times H sub F, where H sub F stands for the heat of fusion. So that formula from reference table T is Q is equal to M times H sub F, where Q is the energy. This is the energy in joules. M is the mass in grams, and then HF is what we just talked about. It is the heat of melting, the heat of fusion in joules per gram. We're going to rearrange this to solve it for heat of fusion. If we rearrange it, solve for heat of fusion, we get heat of fusion is the energy divided by the mass, which is what should make sense, because if it's energy measured in joules and the mass is measured in grams, this should make sense of how you would calculate it. Now, these heat of fusions are constants for different substances, and for water, that constant is 334 joules per gram. We can find this on the reference table B. The heat of fusion for water is 334 joules per gram. So that can be found on reference table B. When can you use this equation? You can find this equation whenever you need to find out the energy it takes to melt ice. So you use it when you need to find the energy required to melt some ice. Key word is you only use it while there is a phase change from the solid to the liquid. All right, let's talk about another phase change, which is heat of vaporization. Right, this vaporization is a fancy word for boiling, and this is a similar definition. This is the energy required to boil 1 gram of a substance. The formula for this can be found on reference table T. If we look at reference table T, it is Q equals M times H sub F, or V, sorry, H sub V. So the symbol here, let's put that in there. The symbol here is H sub V, the heat of vaporization. The unit again is going to be joules per gram. And that equation that we saw is Q is equal to the mass times the heat of vaporization. So that's the energy is equal to the mass times the heat of vaporization. If we rearrange it so that this is solved for H sub V, we're going to get Q over M, which again should make sense because Q is energy that we measure in joules, and M is mass, which is measured in grams. So that should make sense. Now for water, the heat of vaporization is a constant. It is 2,260 joules per gram, and we can find that on reference table B. The heat of vaporization for water is 2,260 joules per gram. When can you use this equation? Whenever you are, if you're trying to find the energy of something while it's boiling. So whenever you are turning something from a liquid into a gas, the energy required to turn a liquid into a gas. All right, the heat of sublimation is another phase change that we can look at. Sublimation is when you go directly from a solid to a gas, right? So this is the energy required to sublimate 1 gram of a substance. The symbol here would be H, capital H, with a subscript of S. So the heat of sublimation. The unit again would be joules per gram, right? It's the same concept, it's just a different phase change. This one's not on the reference tables, but just it's similar enough that it shouldn't be too much of a stretch for you to figure it out. The formula, as you might guess, is Q is equal to M times H sub S. If we rearrange that to solve for the heat of sublimation, we're going to get Q over M. Now it turns out that the heat of sublimation of ice or water from the solid form to the gas form is going to require a lot of energy, 2,838 joules per gram. Okay. So you can see it gets progressively it takes more energy from melting, where you're only going from a solid to a liquid. You're not separating the particles very much. When you are boiling from a liquid to a gas, you are separating the particles quite a lot, and you're again separating them even more so going from a solid to a gas, so it takes more energy. So you'll use this equation whenever you are trying to find the energy required to go from a solid directly to a gas. All right, let's put this together on this graph. We've seen this graph now several different times. Let's get the whole thing in the screen. Sorry if that made noise on the screen. All right, so what do we know so far about this graph? We're going to add some things in here. We know that the x-axis is heating over time. We know that on the y-axis we have temperature. Okay. We know that, let's go ahead and label some of these things. So we're going to label this first point A, and then we're going to draw a line down here. Try to draw as straight a line as possible. We'll call that B. Straight line from the next point, we'll call that C. From the next point, let's draw that in. That's D. We've got E. And then we have one last one way over here, and we'll call that F. Okay, so that just helps us kind of section out the very different parts of this graph. All right, so here, let's do it over here on the y-axis. Let's read over from this plateau right here. This, well, we'll come back to that. We'll come back to that. So here, then we've got this one over here. Let's mark that one. That's another special thing that we need to take note of. Okay, so what do we have here? Typically, when you have three segments where the temperature is increasing, this is where you're going to find your pure states of matter. So here we're going to have only a solid. Here we're going to have only a liquid. Here we're going to have only a gas. On the first plateau, then, this is where the solid will transition to a liquid, right? That's known as melting, or as we now know, fusion. And then in this next plateau here, going from a liquid to a gas, that is where the liquid will turn into a gas. And of course, this is known as boiling, or a more technical term of vaporization. Okay. We also know that in this section we have changing kinetic energy because the temperature is changing. In this segment, we know that we have changing potential energy. The temperature is not changing, but energy is still being added. So we know it's changing potential energy as the solid turns into a liquid. This next phase, where the temperature is changing again, that means kinetic energy is changing. In this segment, the temperature is not changing. All the energy is being put into turning the liquid into the gas. So that's a change in potential energy. And then the last segment here where the temperature changes again, that's a change in kinetic energy. Okay, so these are the things that we know so far. And of course, if we need to label this first plateau where melting or fusion is taking place, this is what we know to be the melting point temperature. We don't have any numbers associated here, but whatever temperature number this is, that would be the melting point. Sometimes we abbreviate it as MP just for convenience. Where boiling is happening, that temperature, whatever temperature that might be, we're going to call that the boiling point temperature. And sometimes we refer to that or abbreviate it as BP. All right, so this is what we've worked with so far. These are all the big things that we know about this graph. But now we are going to add on the final layer, which is calculating the energy required to do each one of these pieces of the graph. And so I'm going to go ahead and turn the graph this way, right? And I am going to continue this line all the way up here. I'm going to continue this line up here, this line up here, so that we have segments going all the way up the paper as we write in this next little piece. Okay, so wherever we have a change of temperature, that's where the substance is purely solid, purely liquid, or purely gas. Anywhere where the temperature is changing, that's where you're going to use the calorimetry equation. Okay, that's where you're going to use Q is equal to MC delta T. Because we have changing temperature, this equation will allow us to calculate the amount of energy the given mass will absorb. So to find the energy from point A to point B, you would use Q equals MC delta T. The delta T would be the difference in the temperatures on the graph. The mass would be given to you in the problem is how much mass a substance has. And the C, the specific heat, right? C is specific heat. And many of the problems we work with is water. And so the specific heat of water, when it's a solid, is 2.09 joules per gram degree Celsius. So that would be a constant. If you were working with water, this is the constant that you would plug in for C, because it's a solid, and that's the specific heat of water when it's a solid. Well, when this other segment of the graph where the temperature is changing, where it's a liquid, this is also the calorimetry equation, Q equals MC delta T. The temperature change would be the difference in temperature from the boiling point down to the melting point. The mass is given of the substance. And then the C is the specific heat of water. But where this was the specific heat of water when it was a solid, the specific heat of water when it's a liquid is 4.18 joules per gram degree Celsius. So that's the number you would plug in for C if you're doing a calorimetry problem while the substance is a liquid. When the substance is a gas and the temperature is changing, you can still use Q equals mc delta T. But the specific heat of water when the substance is in the gas form has the same specific heat as when the substance is a solid, 2.09 joules per gram degrees Celsius. So that's the specific heat you would plug in for C if you were trying to figure out the amount of energy a substance has while it is purely in the gas phase. All right, so far what we have is a chart. I'm going to turn it back this way so we can see the whole thing at once. So far we have a chart that allows us to figure out the amount of energy it takes to heat up a substance while it's in the solid phase, while it's in the liquid phase, and while it's in the gas phase. But what about when the substances are in the melting phase change or in the boiling phase change? There's no temperature change, so you can't use the calorimetry equation. Well, this is where you use the equations that we just learned about. Right? This is fusion, this is melting, so you would use the heat of fusion equation that we just learned, right? Which is Q is equal to the mass times the heat of fusion, where the heat of fusion of water is on the reference tables as 334 joules per gram. So that's the number that you would substitute in for the heat of fusion. If this, of course, we're assuming you're working with water, and then you'd plug in the mass of the water, and that would tell you how much energy it takes. Okay, so that's the equation you would use whenever you are at the melting point of a substance. The equation you would use when you are at the boiling point of a substance is the heat of vaporization equation, which is Q is equal to H sub V. Let's start those, keep it consistent. Q is equal to the mass times H sub V. And the heat of vaporization for water on the reference tables is given to you as 2260 joules per gram. So that is the value of the heat of vaporization that you would plug in here to find the amount of energy required by a certain mass of a substance while it is at its boiling point. So let's bring it all together. If you wanted to find the energy that it takes to start with a solid substance at a low temperature below its melting point, and you added heat to it until some point where it was completely boiled away, if you were trying to figure out the total amount of energy it takes to do all of that, you would actually have to do 5 equations, solving for Q for each one, and then add them up. That's not a typical problem that you'll see assigned by me, but that is how you would approach that. So heating curves can be broken down by their segments because different things are going on at each one of these segments, and each one has a different way to calculate the energy. So you have to pay attention to the conditions of the problem so you know which equation to use and which constant to use in that equation. All right, so in this lesson, just to bring it back, remember what we've done is we've explored how you measure the energy of a phase change. And depending on whether the substance is melting or boiling or some other phase change, you have to take into account the slightly different equation and the slightly different constant that you plug in. All right, that's it for now. We'll see you back in the classroom.